Alright, you've seen the cinematic version, all glowing edges and smooth moves. Now here's the real deal, straight from my desk. Wires, misprints, and a few design regrets included. It's not perfect, but it works. In this video, I'll walk you through the full build, how I designed it, what went wrong, and what actually worked. And if you stick around till the end, you'll see the arm in action with real-world demos. This robotic arm was designed to be simple, modular, and easy to build. I focused on making it educational and expandable from the beginning. Every component, including some very small moving parts, was printed in-house using PETG. That made it easy to iterate and test, though it did come with its own challenges. One of the highlights of this design is the sun gear mechanism in the base. It allowed for smoother motion and more compact torque delivery, something I hadn't tried before. It was tricky to get right, but the result is a smooth, consistent rotation that makes the base feel surprisingly stable for a printed system. Thinking mechanically and incorporating bearings to reduce friction was a whole new way of approaching design for me. This robotic arm has 4 degrees of freedom and uses a total of 3 sun gear mechanisms, not just at the base, but also in other key joints, making the overall motion more compact, balanced, and mechanically efficient. Before we dive too deep, here's a quick look at how the sun gear system works, because it's kind of the heart of this arm. Think of it like a mini solar system. The motor spins the sun gear in the center, which drives the planet gears around the inside of a fixed outer ring. It's a smart way to squeeze smooth, gear-reduced torque out of a small motor, compact and surprisingly powerful. Since everything was 3D printed, including structural joints and moving elements, I had to account for material weaknesses, plastic flexes, and sometimes in ways you don't want, so I worked around that using thicker parts, tighter tolerances, and reinforcement where needed. I also originally designed a 3D printed gripper with a fairly advanced mechanism, which looked great on paper, but once assembled, it turned out to be too heavy for the arm to handle safely. Rather than risk damaging the joints with excess load, I've put the gripper aside for now and plan to redesign it smaller and lighter before attaching it in a future version. That said, I've made a separate video showcasing how it works, with a full breakdown of the mechanism and a working demo, so feel free to check that out if you're curious. For control, I started out with an Arduino Uno, using TMC stepper drivers and basic serial commands. I originally tried using an Arduino Mega with a ramps board, but I accidentally shorted the circuit when connecting a servo and ended up frying 2 Arduino Megas and the ramps itself. So for now, I've gone back to basics, Uno plus breadboard with TMC stepper drivers. In future builds, I plan to design a custom PCB so I can ditch the flaky connections and move towards something more permanent. At first, I used a stepper motor for the elbow joint, but it couldn't lift the weight properly, so I swapped it out for a continuous 360-degree servo. But that created other issues. I also had to redesign the mount, since the original frame was built to hold a stepper, not a servo. Since the servo only rotates continuously, it doesn't offer the same positional control, which made the elbow's motion jerky and unpredictable. Meanwhile, the base rotation, driven by the stepper and sun gear, ended up being much smoother by comparison. For future versions, I'll be switching back to a stronger stepper motor with higher torque output. I'll just need to adjust the frame slightly to accommodate the larger form factor. That change should bring more stability and precision to the elbow joint, and smoother movement as it still uses the sun gear mechanism to transfer torque efficiently. The arm accepts basic serial commands, like UST 500, to move each joint. You can also send multiple commands simultaneously, for example, UST 500, BST 400, which lets the motors move in sync for smoother, coordinated control. There are still bugs to iron out, but I plan to migrate everything to ROS for more advanced control logic and integrate Wi-Fi connectivity to support remote control in future versions. The Sun gear mechanism really exceeded expectations. It delivered consistent motion and absorbed more load than I anticipated. The stepper motor system for the base and shoulder was also super reliable, and overall, the form factor looks great. It's compact, clean, and functions well as a prototype. Plastic Flex introduced wobble and reduced precision. The continuous servo offered poor control, especially for anything requiring exact angles. Breadboards were another weak link. They came loose during movement, and having too many fused parts made maintenance unnecessarily difficult. In the next build, I'll focus on modularity, detachable joints, reinforced load-bearing parts, and a lighter, smaller gripper at around half the weight. I'll replace the 360 servo with a higher torque stepper, strengthen the elbow joint, and move to custom PCBs to eliminate loose connections. I'm also planning full integration with ROS and Wi-Fi for smarter, scalable control, so in theory, I could operate the arm remotely while sipping a flat white on a beach in Santorini, as long as the Wi-Fi holds up. This was a massive learning experience for me, not just about robotics, but about problem solving, patience, and the value of iteration. It's far from perfect, and that's exactly why I wanted to share it. I'm keeping this version uncovered so you can see all the internals as they are, imperfect but real. I've got more builds and experiments coming soon, so if you're into robotics or DIY design, consider subscribing and be part of the chaos, growth, and occasional magic.